아, 아, 헬로. 아, 아, 아하, 아, 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 아. Hello, everyone. 아, 아,
에코가 문제구나. I don't know why. Austin. Hi. Yeah, red.
in the comfort of your own home. Order and pay on our app or at ogtogo.com. Choose from all.
Okay, how's your semester going? Not bad. How's your semester going? Your semester is going. Uh-huh. Great. Mm-hmm. Mm-hmm. Great. Yes, in-person courses over before the Thanksgiving break holidays, so you can go back to your home, at least in the Thanksgiving. But I think that final will be held in person or or online. It depends on the system the provost actually adopt. So actually, the university wants to adopt kind of the online AI-based proctoring system. So it is not, cleared. So I just wanna catch up. But if it was adopted, then you can take your final on your home. Otherwise, you need to go back to college station. But let's see. Yeah. So university's policy is just adopting this on the second midterm so that you can take your exam in your home or whenever you are fine, right? So yeah. And I also hope to go back to home in Thanksgiving. So I really want to that happen. Oh, and I just wanna unofficial announcement that I see that in the some I just prevent echo. Yes, some of you had not get the full credit on the website, and since this is the courses that actually each midterm has different topics, right? So it is not the cumulative topics. So if you didn't get the full credit on your website homework, then it is a little bit difficult to get thing over your midterm or your in the your grade overall grade after the class. So if you think that if you are not understanding some of the problem, or if you just got if you lose credit but you don't know why, then please ask me, and please ask me to extend your homework due date or give me one more trial so that you can review it. Or also, yeah, so that what I hope is that you can earn 3 points on your computer homework, right? In the website homework, and before the midterm. So that, and I think that in my experience, it will be helpful for you to get a good score on the midterm, but also you can get a good score for overall classes. So if you had any missed homework problem, or if you don't know how to solve it, then please ask me to extend your due date, or ask me one more trials or something else, right? Okay, great. Bless you.
No, I lied. He's not on here. Oh, no, yes, he is. Look at him. Yeah, but I'm not going to no fucking class. Yeah, that's another thing. I ain't gonna be on Zoom.
Okay, hello everyone. So today I have two announcements on the course. So first announcement is about the quiz, which is actually what I said, video quiz. So what I think is that I will give you some recommended number of problems in the textbook, some recommended problems. Then just choose one and take a video, maybe 2 minutes or 3 minutes is fine, to explain, which explains the solution, right? Explaining solution. And then please upload it on eCampus.
Do you mind sharing your screen with us?
Oh, you can, sorry, I need to share. Thank you very much. Give me a second. Yes. Yes, sorry. I need to share this. Okay, so what I say is that I will give you some programs in the chapter 2, in the textbook chapter 2 today. So it will be announced on the eCampus and in the email. And just choose one of them and take a video explaining your solution about the problem, then upload it on the eCampus, or if you think the eCampus is too slow, then just upload it on YouTube and give me a link in the eCampus, right? So yeah, if you choose the option for YouTube, then there are an option called unlisted. So or YouTube. Unlisted means that only someone who have the link can see your video, right? So it is not on public. So unlisted video. And so if you just give me a link, then you're fine. And yeah, and Lindsay says that does it need to be a certain chapter? Yes, it should be on chapter 2 because we will deal with chapter 2 in this week. So it should be on chapter 2. And due date is Thursday. So I will give you a program on tonight. And your due date for this quiz is Thursday night before 12 p.m. So I'll make it clear. Due date is Thursday midnight. I still confusing them whether 12 p.m. is midnight or 12 a.m. is midnight, but okay. So anyway, midnight. Okay. No, no, you don't need to speak me directly, just taking your picture for explaining something. So what his question is that, can you need to meet in Zoom via the, online? But no, you don't need to do it. So just taking your video using your cell phone or whatever your device, then just upload it to the eCampus or YouTube. That's fine. Pardon? Yes, you can record it via Zoom, then you can just give me a link. Yeah, then that's fine. Yes. Okay, great. And is there any other question? Okay. Yeah, it is take-home quiz. Yeah. Yes. So it is take-home quiz. Yes. Oh yes, I will give you some recommended programs tonight by email, or you can post and just choose one of them. Oh yes, yeah, if you don't have textbook, then I will just give the chapter, programs. So. Mhm. Yes, I will grade. So grade scheme is that, first of all, yeah, I need to definitely thank you for asking this. Grading. So what she asked was about the grading scheme of this video quiz. So it is definitely 10-point based, and 5 point is just introduce your name, please, because I need to remember your names. Yourself briefly, just your name is fine. Name and which program you serve. And for 3 point, it is, I just, thinking about your flow logic. So what I mean flow logic is like this. For example, some program requires to find the Hamiltonian circuit of a graph. So for example, then your flow logic is that definitely Hamiltonian circuit is your circuit having all vertices. So to find the Hamiltonian circuit, we can just directly choose some edges. So if you just see these edges, then it forms a circuit. So that's your Hamiltonian circuit. So like this. So you need to explain why your answer is true, right? Okay. Pardon? Oh, how many minutes you need to speak? So yeah, if you can solve it by just a second, then it's fine. But usually I think that I will just choose some program requires you to use at least 2 minutes. So, or 2 or 3 minutes. So yeah. Oh yeah, after solving it and after understanding it completely, then you can take your video. Right. That's a good question. Yes. So what the question is that, do you need to record your solving, or after solving everything, then you can take video? So my answer is just the latter. So just solve it everything and understand it completely, then take a video. Right? Yeah, just one problem. Only one problem is fine. Or if you want, then you can send two problems, but yeah, one is fine. Right. So yeah, grading scheme for 3 point is pro logic, and 2 point is from the answer. And also, I promise that, yeah, definitely it takes some time, but I promise that I will give you feedback for one-to-one, right? So yeah. I will, yes? Yeah, if you wanna have 2, then yes, I will give you some bonus points. Okay. So what he says is that if you do just solving 2 programs, they can get credit. So I say yes, I will give you some bonus points if you want. Yeah. Let's think. Yeah, maybe I can replace one of your quizzes for that credit. So if you just to solve 2 programs, then maybe I can just delete the one of your lowest grade on the quiz. So is it good? Great. Yes. Okay, great. Good there. Okay, so do you have any other question, please? Good. And yes. Okay, so that's first announcement. And second announcement is the midterm. So it is September 15, Tuesday, at the same time of the class, PM to 45. So either have 12 to problems and chapter coverage is from chapter 1 to 3. So just, yeah. I will give you more detail when I write down all the problems. So I'm just currently making midterm exams. So, but just let you know, right? Okay. Do you have any question on the midterm or anything else? Okay. So what's your question is that we need to go to class or you need to be home, and definitely you need to go home or any places other than classroom. So in the university policy, yeah, all midterms or all finals should be, taken in the home. So yeah, in that case, so you need to go, you need to be here to take your exam. Okay, great. Pardon? No, you don't need to take exam on here, right? Because first of all, at least you cannot have two devices proctoring, right? So that's why we don't need this classroom. So please go some places or some find places that have a Wi-Fi, and also you can take some kind of second device proctoring. So yes, then that's fine, right? Yeah, exam will be proctored by me via Zoom. So that's why I need to require you to have a second device. Pardon? But that's the university policy for midterms. So in the quiz, I can do it, but in the university policy, they require the BYOD, which means that bring your own devices, and it contains two devices. One is laptop and one is cell phone, so taking pictures. So usually I just proctoring via cell phone, so that each cell phone I can see you and your desk and your laptop. So it's simultaneous. Yeah, get on Zoom on your phone. Mm-hmm. Yes. Mm-hmm. Yes. So yeah, that's why we need some desk instead of this one, but use actual desk. So in the last semester, some of the students actually put some books in the desk and just put your iPhone like this, then watching, yes, desk and something simultaneously. So maybe you can do such a policy, or if you have any other devices like, selfie camera, a selfie stick, then you can just put your selfie stick on your desk, then you're proctoring it. But yeah, but usually book works. And Joanna says that, will we have a review before the midterm? Yes, I will give you a review before the midterm, but I'm not promising that, yeah, the review will be given on the actual classwork, actual class. So yeah, if I don't have time, then I definitely give you some review in other sessions, right? And Hannah McLaren says that, so we will log into Zoom the day of our exam with your phone and take the exam with our laptop. Yes, that's what I want to say. Yes. Okay. Do you have any question? Okay. Okay, great. So now let's get back to the actual math. So in the last time, we learned about the Hamiltonian circuit. So Hamiltonian circuit is a circuit containing all the vertices of graph. And complete graph is a graph for any, if you just pick any of two vertices, then it has an edge, right? So this ABCD is an example of complete graph with four vertices. And this triangle is an example of complete graph with three vertices, right? So do you have any question on what the Hamiltonian circuit or complete graph? Okay, then also we learned about the notation factorial, which is an exclamation mark. And it denotes just multiplication n times n minus 1 times n minus 2 times blah, blah, blah times 2 times 1, right? So 1 factorial is just 1. 2 factorial is just 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6, right? And then there are some theorem about how many numbers of Hamiltonian circuit in a complete graph with n vertices. So Peirce theorem says that there are n factorial Hamiltonian circuits in a complete graph. And you can see it using this example. So for example, first of all, you can choose an edge by 3 possible ways. So there are AB, you can choose AB, and you can choose BC, and you can choose AC, right? Then after you choose one of the edge, then for example, if you choose just this edge AB, then there are two possibilities to choosing BC or choosing AC, right? So you need to multiply 2 in here. And after you choosing the another edges, for example, if I choose BC, then there are only one possibility to make a circuit, right? Which is just AC, right? So it should be one possibilities. So that's why we have 3 factorial Hamiltonian circuits in a complete graph of 3 vertices, right? Does it make sense, or do you have any question on this? Yes, n is always equal to the number of vertices, yes. Right? So let's find it, yeah, the actual Hamiltonian circuits. So for example, first you can choose AB first, or you can choose BC, or you can choose AC, right? Then after choosing AB, all you can choose is BC or AC, right? So here you can choose BC or AC. And after choosing BC, you can choose AB or AC. And after choosing AC, you can choose AB or BC, right? And in the third step, after choosing AB and BC, and there is only one edge remaining, which is AC, right? And after choosing AB and AC, the only one edge remaining is BC. And likewise, if you choose BC and AB, then only one edge remaining is AC. Then if you choose BC and AC, then the only one edge remaining is AB. And if you choose AC and AB, the only one edge remaining is BC. And if you choose AC and BC, and the only one edge remaining is AB, right? So for each one gives us Hamiltonian path. So AB, BC, AC gives you ABCA. and AB, AC, BC gives you the BACB, and BC, AB, AC gives you CBAC, and BC, BCAC, AB gives you BCAB, and AC, AB, BC gives you CABC, and AC, BC, AB gives you ACBA, right? So these are 6 different Hamiltonian passes. So yeah, that's why we have such a Hamilton, 6 Hamiltonian passes in the complete graph of 3. Oh, sorry. Okay. Yes. Do you have any question on this? Good. Okay, then from this, you can find some kind of meter of the Hamiltonian path. For example, thinking about ABCA, it means that just from A to B, B to C, C to A, right? But actually, this is the same as A to C, C to B, B to A, right? So in this case, which is ACBA, right? So this one and this one is just the same path with starting point, but it is just going reverse way, right? So in that case, we can see that those two are in mirror image between them, right? So one of them is just mirror. So in that case, there are n factorial dividing by 2 Hamiltonian circuits in the complete graph if a circuit and its mirror image are not counted as the separate circuits, right? So if you're just thinking that circuits only for one circuit, and if you're just thinking each mirror image as the same circuit, then there are 1 circuits and 2 circuits and 3 circuits, right? Because BACB, which is BACB, for example, is the same as BCAB, but with reverse. So BACB is just clockwise order, but BCAB is just counterclockwise order, right? So likewise, CBAC is counterclockwise order, but CABC is the same circuit with clockwise order, right? Okay, do you have a question? So I will specify what number I want to. Yes. So I already specify Hamilton. Yeah. If I just said that to find all Hamiltonian circuits in a complete graph, then I also specify that you need to count a mirror image as a separate one or not. Okay. Great. Great question. Okay. Do you have any other question? So what she says is that in the exam, should I ask about the which number we need to use, and what I answer is that I will always specify when you need to circuit and mirror image are counted as a separate circuit or not. Okay, that's my answer. Okay. Do you have any other question? Great, right? And if a starting point is specified, what I mean specified is just fixed, then there are n-1 factorial Hamiltonian circuits in a complete graph, right? So for example, if you just starting point specified with A, then there are only 2 Hamiltonian passes, ABCA and ACBA, but it is just 2 factorial because 2 factorial is just 2 times 1. And Laney questioned, are there 6 Hamiltonian circuits or 3 because of mirror imaging? So if we just counting mirror image as a separate circuit, it has 6 Hamiltonian circuits. But if we count mirror image as a not the same circuit with each original circuit, then it has 3 Hamiltonian circuits. So, and we always be specifying that whether we count circuit as the same as the each mirror image or not. So that's what I say. So it will be already specified on the program. Does it answer your question, Lainey? Thanks. So yeah, so in that case, when if your starting point is specified, then for example, if your starting point is specified, then all you need to do is just choosing the other points except the starting point, right? So if you just finding the Hamiltonian circuit with the complete graph with n-1 points, for example, in this part, then all you need to do is just adding an edge from your circuit to A and go back to your circuit. So that's why we have n-1 factorial Hamiltonian circuit when your starting point is fixed. Does it make sense? Or do you have any question? Good. Okay. Great. And again, if the starting point is specified, and also if we didn't, if we circuit and its mirror image are now counted as separate circuits, then all you need to do is just dividing by 2. So for example, in this example, if we just specifying A as a starting point, then there are 2 Hamiltonian circuits, but they are just mirror images to each other. So all you have in the Hamiltonian circuit is starting A and doesn't count your mirror image as a separate one. And there are only one Hamiltonian circuit, which is ABCA, right? Okay. So does it make sense, or do you have any question? Good. Great. So let's deal with some examples. So in the example 1.13, so for complete graph with 6 vertices, how many Hamiltonian circuits are there? And yeah, if you just asking this without any mention about the separate circuits or mirror image, then it's just counting every Hamiltonian circuit and counting mirror image as a separate circuit. So in that case, it is just 6 factorial, which is 6 times, 5 times, 4 times, 3 times, 2 times 1. And if you just calculate this one, then you can get 720, right? And next question is, how many different non-mirror image Hamiltonian circuits are there? So how many different non-mirror image means that we didn't count each mirror image as a separate circuit. So in that case, what you need to do is just dividing your 6 factorial by 2. Then what you can get is 316 edges. Do you have any question? Okay, great. And how many Hamiltonian circuits are there starting at the vertex A? So here, again, using your formula, you can just divide your 6 it is just 6 minus 1 factorial because our starting point is specified with A. So which is just 5 factorial, which is 5 times 4 times 3 times 2 times 1. And if you just calculate this, you can get 120. And to count how many different non-mirror image Hamiltonian circuits are there starting at the vertex A. So again, you can just divide your 5 factorial by 2, which is 60. Right? So I just applied the theorem to finding out these questions. So does it make sense, or do you have any question? Okay, great. So let's find the all different non-mirror image Hamiltonian circuits for the complete graph below starting at A, right? So first of all, we know that actually our starting point is fixed as an A, and we will find all different non-mirror image. So it should have 4 minus 1 factorial over 2, which is 3 factorial over 2, which is just 3 times 2 times 1 over 2, which is 3, right? So we know that there are only 3 Hamiltonian circuits by thinking the mirror image as not the separate circuits. And to find this, since we know that our starting point is A, so just choose A first. Then you can go B, C, D, right? Because yeah, the B, C, D are all points you didn't visit before. And if you just choose B, then all you can go is C, D, right? And if you go to C, then all you can go is B, D. And if you go to D, then all you can go is B and C. And if you already visit A, B, C, then you need to go to D and you need to go back to A. And if you already visit A, B, D, then you need to go to C, then you need to go back to A. And for A, C, B, you need to go back to, what is that? D and A, C, D, B, A, D, B, you need to go to C and A. For A, D, C, you need to go to B and again come back to A, right? So these 6 Hamiltonian circuits with counting mirror image as a separate one is A, B, C, D, A, B, D, C, A, C, B, D, A, D, A, C, B, A, C, D, B, A, sorry, A, C, D, B, A, D, B, C, A, D, C, B, A. And now we need to figure out just deleting the Hamiltonian circuit with mirror image. So first of all, the mirror image of ABCDA is ADCBA, which is this one, right? So this one and this one are mirror image. And the mirror image of ABDCA is ACDBA, which is the first one. And mirror image of ACBDA is the mirror image of ADBCA. So there are 3 circuits. First one is ABCDA or ADCBA. And the second one is ABDCA or ACDBA. And the last one is ACBDA or ADBCA. Right? So that's the 3 Hamiltonian circuits we want to find. Okay. Do you have any question on this brute force method? So it is called brute force method because we just investigate all possible circuits, right? So it is just definitely just attack something for completely. So that's why we call it as a brute force method. Okay, do you have any question on this method? Okay, great. So it is easy for the graph with 4 vertices, but it is a little bit difficult to find brute force method to find all different non-mirror image of Hamiltonian circuits. But let's do it. Yeah. So start with A. Again, we are starting with A. Then you can go to 4 other places, B, C, D, E. And if you go to B, A, B, then you can go to C, D, E. Or if you go to C, then you have 3 possibilities, B, D, E. If you go to D, then there are 3 possibilities, B, C, E. And again, if you go to E, then there are 3 possibilities, B, C, D, right? Then for C, there are 2 possibilities, D, E, and C, E, and C, D. Yeah, C, B, D, E. Okay, I need to write down more bigger than this. Okay, give me a second. Sorry. Okay, DE. And here you have 2 possibilities, BE. And if you choose ACE, then or 2 possibilities BD and ADB. You can have possibility CE. For ADC, you have possibility BE. And for ADE, you have possibility BC. And okay, I will write down it more below. Then for B, you have possibility CD and BD and BC, right? So that's quite complicated. But after then, the all possibility is only 1 because you already choose 4 points. So there are all possibility you have is just go the remaining point and go back to your home, which is A. So for A, B, C, D, you need to go to E because there are only remaining points you didn't visit is just E, and you go back to home. And for A, B, C, E, you have DA. For A, B, D, C, you have to go E. For A, B, D, E, you have to go to C. So A, B, E, C, you have to go to D. A, B, E, D, you have to go to A. B and A. Oh, we already visit B, so sorry. In this case, we need to visit C, right? And for ACBD, we need to go to E and A. ACBE, you need to go to D. ACDB, you need to go to E. ACDE, you need to go to B. And ACEB, you need to go to D. ACED, you need to go to B. ADC, ADBC, E, ADBC, C, ADCB, E, ADCE, O2B, ADCB, C, CB, D, C, yeah, D, B, C, B. So there are 12 for choices because we already picked the A. So 5 minus 1 factorial is just 4 factorial, which is 12 for choices. So from here, what you can get is A, B, C, D, E, A, B, C, E, D, A, B, D, C, E, A, B, D, C, A, B, E, C, D, A, and so on. I will give you the full graph, full answer after the class as a complete note. But do you know how you can do for this brute force method, right? So just write down our possibility and just write down our answer, then figure out its mirror image, right? So as you can see, this is quite difficult, not difficult, but quite tedious job, right? So you can see, so even for complete graph with 5 vertices, it is very tedious. Pardon? That's what we run for next chapters. So yeah, that's why the reason I introduced this brute force method is that actually it is the optimal, it gives you optimal path, but it's very difficult and very tedious, right? So in the next chapter, we will run. Right now, here it is just counting how many numbers of Hamilton passages are there, right? Mm-hmm. Yeah, in the exam, I promise you that I do not give you brute force method until the graph is very simple or yeah, anything else, right? Yeah, not that big, not that big as 5, right? And there are some questions from Morgan that did anyone else want to die when doing this homework? Okay, yeah, I understand completely. So in the next section, we will learn how to find this kind of method for efficiently, right? Because, you know, in the real world, if you're thinking about the, actually this problem is important because we wanna deal with the real world problem called traveling salesman problem, right? So the traveling salesman problem is the problem finding a least cost Hamiltonian circuit in a complete graph where each edge has been assigned a cost. And the reason we say it as a traveling salesman problem is this. So for example, maybe, yeah, after 10 years, maybe you just buy the Amazon. So now instead of Jeff Bezos, now you are the CEO of the Amazon. Then you need to maximize your profit by choosing some efficient way to visit all of the city in the America, right? Because the Amazon deals with a lot of products, so if they need to make some profit, then they need to optimize this kind of cities. So for example, definitely you don't want to go from the Los Angeles and New York and again San Francisco and again Boston. You know, that's not the optimal path, right? So to avoid such bad choices, we need to find an optimal circuit which the salesman can visit every city in once, but still have the least cost, right? So, and to deal with this, there are some algorithms called heuristic algorithms. So that's the division 2.2. So heuristic algorithm is some algorithm which are faster to solve. However, the result may not be optimal, right? So this is some algorithm which gives you the best solution, but it may not be optimal, right? So for example, we can deal with this example 2.1, right? So the example 2.1 means that use the brute force method to find the least cost Hamiltonian circuits. But as you can see, it is very distressful, right? Even if in that case, we need to add some weights on the edges for finding which one is the least Hamiltonian cost, right? But instead of doing it, maybe if you see the numbers, then you can find some, not that may not be the optimal, but at least you can find some efficient way of visiting all the cities. Can you find it? How can you visit all these 5 cities at once, but still with the minimal cost or minimal rates? Surrounding edge. Great. Why do you think that surrounding edge gives you some optimal solution? Great. What's your name? As Rafin said, yeah, if it's just watching these rates, then these are all some 12, 14, or 10 plus something, right? But all the other edges inside is 13, 29, 25, 27, and only 13 is, seems to be, in the below, but all other edges are definitely greater than the other edges. So maybe we just want to avoid you use these things. Then, one of the intuitive solution is just surrounding these all edges, right? So, so one of the Hamilton circuit is just A, B, C, D, E, A. Since edges inside of the pentagon seems heavier weights to have weights. Then those in the boundary, right? But can we make sure that this surrounding is the optimal? Can you? Yeah, maybe you can use the brute force to showing that, oh, this is optimal. But is there any other way to showing this one is optimal? Pardon? Yes, yeah, without adding all the ways, is there any other ways to finding that what Love saying is surrounding the order of the circuit is the optimal for all Hamiltonian, more than all Hamiltonian passes? Yes. So my question is, how can we show that this Hamiltonian path just going around the boundary has the least weight compared with other Hamiltonian circuits without calculating all the weights of the Hamiltonian circuits? Does it make sense? Okay. Yeah, I just want to avoid brute force method because it is very distressful. Yeah, but do you have any clever way to solve it? I will leave it as your exercise, but if you can solve it, then I will count your first quiz as the free credit, right? Okay, so just thinking it. But there are some methods to finding this and some heuristic method. Actually, what Loving is used is one of the heuristic method called nearest neighbor algorithm. So he intuitively knows what it is. So it is just nothing but finding very simple algorithm. So just fixing the home city, then visit the nearest city first, and visit the nearest city that has not already visited, and repeat until you have the circuit, right? So for example, in this example, in the starting A, also our home is A. So the one thing you can do is just AB. Then actually, according to the theorem and the algorithm, you need to go E. Then you need to go D because 16 is the most least wedges, weight edges. And then you need to go to C. Then you need to go to AC, right? Yes, so you cannot go back. So if you just visit one of the city, then you didn't go back to that city. Pardon? Oh yeah, so I start with A, right? So there are 4 possibilities. One is 15, and the other is 27 from to C, and the other 13 go to D, and other is say 17 go to E, right? But you know that 15 is the most nearest one, right? So that's why I choose this 15. Oh, sorry, I just choose with yellow wedge. Then from B, there are 3 possible choices. One is BE, which is 13, and BD, which is 25, and BC, which is 14, right? So in this case, 13 is the most nearest one. Pardon? Oh yeah, so it is actually specified on the program. Yes, so in this algorithm, you always just put some starting point. So starting point is fixed, then you can use that algorithm. Right? So that's okay. So let's deal with some example like this. So for example, this is example of nearest neighbor algorithm, heuristic algorithm. So for example, in this complete graph with 4 vertices, use the nearest neighbor algorithm to solving the TSP program, starting at Miami, right? Then starting at Miami, there are 3 possibilities. One has distance 2, one has distance 4, and the other has 3.5. So we need to choose Veracruz because Veracruz is much more near than Barbados or San Juan. Then after going to Veracruz, you can have 2 choices. One has distance 6 and one has distance 8. So just choose the diagonal one because 6 is less than 8. Then all the remaining point is just Barbados. So just go to Barbados and go back to Miami using another diagonal. So your travel plan should be from Miami and taking 2 hours to go to Veracruz and taking 6 hours to go to San Juan and taking 3 hours to go to Barbados and taking 4 hours to go to Miami, right? So all trips will be counted as 2, 6, 3 plus 4, which is 15 hours. So you only take 15 hours to visit all of the cities, right? Does it make sense, or do you have any question? So to deal with whether this solution is optimal or not, yeah, in this case, we need to use the brute force method. So yeah, but in that case, for example, there are only 3 possibilities, right? Because Miami has, so we already know that Miami is a starting point. So first possibility is Veracruz and San Juan and Barbados, and San Juan, Barbados, Veracruz, Barbados, San Juan, Veracruz, then go back to B, SJ, BC, B, BC, SJ, BC, SJ, and go back to Miami. And, you know, in that case, I also hate this kind of tedious job, but to 3.5 and Veracruz to San Juan 6, Veracruz B 8, San Juan to Veracruz, which is 6, San Juan to Veracruz, Barbados, which is 3, Barbados to San Juan 3, Barbados to Veracruz 8, SJ to B 6, BSJ 6, BC to B, BBC, SJ to BC 6, 6, and Barbados to Miami 4, SJ 3.5, Barbados to Miami 3, Veracruz to Miami 2, sorry, 2, 6.5. And again, we need to add all these numbers. Then this one gives you 17, oh no, 18. And this one gives you 19.5. This one gives you 20.5. This one gives you 16.5. This one gives you 15, and this one gives you 21.5. So yes, so the optimal way is just from Miami to Barbados and San Juan and Veracruz and Miami, which is just mirror image of this one, right? So you can figure out that it is optimal, right? Okay, the question. Mm-hmm. Mm-hmm. So the idea to checking this optimality is that I just want you to show that actually sometimes it doesn't give you optimal answer. So in this case, it gives you optimal answer, but sometimes it doesn't give you optimal answer. And I will just show you for next example. So next example is the graph actually we deal with. So to see this, first of all, from starting A, we can find the nearest neighbor algorithm to find the optimal answer for this one, right? So that's the one of the optimal answer. One of the answer from the nearest algorithm when you starting the point is A, right? However, when you start your answer on D, then you need to use this 12 first because 12 is the least weight edge. Then from C, you need to use 13. So because 13 is So not 30, not, sorry, this is not 13, this is 27. So you need to use 14. Then you need to use 13, which is BE. Then you need to use 17. Because 16, if you just use DE, then you just go back to D without taking A, right? But that's not. Pardon? So we B to C and C to B, right? Because C to A has weight 27. Yeah. Okay, great. No problem. Yeah. So. So, and the last way is AD, right? So as you can see, if starting point is changed, then neighbor algorithm gives you different answer, right? It means that at least one of them should be not optimal, right? So it means that one of them should not be on optimal, right? So as Hannah actually asked me the same thing, what Harry says. So every time we do nearest neighbor, we should check our work with brute force method. No, I just show it for the reason that nearest neighbor algorithm may not give you not optimal answer. So that's the example. So as you can see, maybe check this. So for example, I didn't check it by brute force method, but checking the rate of this circuit. So in that case, it is 12 plus 14 plus 13 plus 17 plus 29. And this one is 15 plus 13 plus 16 plus 12 plus 27. So the first one gives you, what is that? 26 plus 13 plus 29, which is 85. And this one gives you 28 plus 28 plus 27. So it is 83. So definitely 85 is greater than 83, right? So this circuit gives you much optimal than this one, right? But can we just compare this with what Robin actually find it in the previous one? So in what he says is that actually just going around is one of the best answer. And if we just thinking about this solution, then weight of your circuit is just 17 plus 16 plus 15 plus 14 plus 12. And it is 33 plus 29 plus 12, which is 64. No, 65. I'm not sure, but anyway, some 60 something, right? So, sorry, I'm not good at counting, but 60 something. But 60 something is definitely better than 80 something, right? So nearest neighbor algorithm may not give you optimal answer. So that's why I want to say what I want to say for these examples. So no. So that's the actually cost of the heuristic algorithm. So if you use heuristic algorithm, then you can get your answer faster, rapidly. However, your solution may not be the optimal solution, right? So that's the advantage and disadvantage of the heuristic algorithm. And the reason we use the heuristic algorithm is that the real world problem is so complicated. So for example, in the United States, there are at least 100 cities in the United States for major cities, only counting major cities. Then, you know, finding brute force on 100 cities is not possible even if you have supercomputer, right? So instead of doing this, you can just solve your problem using this kind of heuristic algorithm to find near optimal solution, right? It may not be optimal, but it is still close to some optimal solution, right? Does it make sense? Okay. Do you have any question on the nearest neighbor algorithm? Good. Okay, great. And this is the one of the important example. So as you can see in the example 3.4, we have a table given the distance between the different cities, right? So there are some cities, Epton, Banuns, Casper, something else. So there are 8 cities, right? And these 8 cities has also some load from the other 2 other cities, right? So actually, this table depicts the complete graph of 8 vertices, right? So this is the important point, that you can turn your complete graph into a table, or you can turn your table into a complete graph, right? So for example, just deal with some example, just complete graph with 3, then maybe you have some of the weights 3, 4, 5, then you can write down it as your table, C, A, B, C, then A to B is 3, A to C is 5, and B to C is 4, 5, right? So what I wrote is just the distance between AB and AC and BC in a table, right? So this table depicts this complete graph, but also you can, from this table, you can recover your complete graph with weights, right? Does it make sense? So these are nothing but the same two representation of the same information, right? That's the important part, right? So if you just accept that these tables and graphs just depict the same situation, then you are fine, right? Does it make sense? Okay, great. Then the question is, if the brute force method was used to find the least cost Hamiltonian circuit, starting at Epton, how many different non-mirror image circuits will we need to be checked? And in this case, it is complete graph of 8 vertices, but it starts with Epton, and with just counting only non-mirror images, which means that mirror images can be counted, cannot be counted as a separate circuit. So it is A minus 1 factorial over 2 circuits should be counted. And in that case, it is just 7 factorial over 2. But you notice that it is 7 times 7,200 over 2, which is 7 times 360. So it is 2,520 circuits should be checked to find an optimal circuit, right? But you know, that's too many costs to figure out every circuit in here. So instead of doing brute force, you can just using the nearest neighbor algorithm starting at Epton, right? So what you need to do here is, again, choose the city which is nearest to the Epton. The first city which is nearest to Epton is Rock Spring, right? Because 180 is smaller than any other numbers except 0. And when you just go to Rock Springs, then again, the smallest city you can visit except Epton is Laramie. Yeah, I don't know what the city is. So this city with L, because 207 is the smallest number except Epton, right? Because we already visited Epton. Great. And then again, from Laramie, the nearest city of Laramie except Rock Spring and except Epton is Pine Bluffs, right? Because 89 is the smallest distance between those cities. And from Pine Bluffs, the smallest distance with the other city, except Laramie, Epton, and Rock Spring, is Newcastle. Yeah, because, yes, Newcastle is the second smallest one. Yeah, and we already visited Laramie, so it is the most nearest one except Laramie. Then from Newcastle, then we already visited Rock Spring and Laramie and Epton. So the possibility to go is just Sleepy Hollow, right? Because 78 is the most smallest number in this table, in this column. And from Sleepy Hollow, we already visited Rock Spring, Pine Bluffs, Newcastle, and Laramie. So there are only two possible choices, Casper or Bannoon, and I think the Bannoon, which is 122, is less than 128. Then the only one possibility you can get is just Casper. Then you need to go back to Epton. So these are the whole numbers you can get, right? So what I did from Epton to Rock Spring, and from Rock Spring to, where is it? Laramie, which is 207, and from Laramie to Pine Bluffs, which is 89, and from Pine Bluffs to Newcastle, 217, and Newcastle to Sleepy Hollow, 78, and Sleepy Hollow to Bannoon, 122, and from Bannoon to Casper, which is 7, and lastly, you need to go back to Epton, which is 356. So that is how to use nearest neighbor algorithm on the table instead of the graph. Do you have any question on this? Mm-hmm. So critical path is actually deal with 2.5. So we will deal with in the Thursday. Yeah. So I Oh, really? Yeah, I extended. Yeah, I extended. No problem. Okay. Good question. Okay. Do you have any other question? Okay, then yeah, I will say extension that because critical path is what we didn't deal with it right now, and in the syllabus we will deal with the chapter 2 in the Thursday. So I will extend the homework. So for homework 2. Okay, so let's call it a day, and thank you very much for hearing. Fine. Really? Ah, sorry, but yeah, I don't know how to say it in English, so actually, yeah, those fancy pronunciations you use for South Korea, so that's why no, I very little. I didn't know much of that. Yeah. Oh, you're Spanish major. Mhm. Oh. Mhm. Great, thank you very much. No, yeah, South Korean, yeah, English, and Spanish a little. Yeah, I actually one of my good friends is in my MS graduate, and he's from Spain. So yeah, he teaches some of the Spanish for me. So that's why I'm a little bit used to. Mhm. Mhm. Yes, you're right. Mhm. Thank you very much. Yeah, I try to do it. Yeah, great. No problem. Yeah. Mhm. Yes, I'm from South Korea. Yes. Oh, really? Great. Mhm. 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 Nice to meet you too. Okay, great. Mhm. Good. Thank you. Yeah. Mhm. 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 So just wait for the pi. So it is not proctoring. So I just want you to present some solutions. So yeah, just taking PyTorch is also fine. Yeah. Thank you. Bye. Have a good day. Yes. Yeah. Yeah. So homework due. So what I say is that sorry. So homework for website should be due in maybe I think that due in next Monday because or next Tuesday or Monday because in the syllabus you can see that chapter 2 will be dealt for the whole week of this week. So I will extend the due date, and for the take-home quiz about taking video, I will give you some recommended program tonight via email and via eCampus so that you can just taking your video for solution. So so these are two different things. So what I mean extending due date is just WebAssign program, but for extending but the video take-home quiz has due date this Thursday. Does it make clear? Yeah, you have due week this week is the just video quiz. Yes. Okay, so okay, thank you, Alexandra. So is there any other question? Okay, if there is no other question, I will have a office hour from 3 to 4:30 p.m. So, okay, please visit that Zoom session for me. Thank you very much and have a great day.